Yesterday we introduced this topic of data transmission, starting to look at signals, and today we're going to continue on and trying to make some more sense of how signals are transmitted. So find your seats. Don't worry about databases and so on. There's no rush. Okay? We saw that yesterday we introduced the basic form of a communication signal, a sinusoid signal, where we can write an equation, S, the signal intensity, say the height of the sinusoid or the signal as a function of time, in general is on one of our previous slides, the peak amplitude A multiplied by sine 2 pi f t, where f is the frequency of that sinusoid, plus the offset, the phase offset, which shifts it along. Those three parameters, peak amplitude, frequency, phase. By changing them, we get different shaped sinusoids, and by combining sinusoids together, we can get different shaped signals. And in theory, any communication signal, we can create a mathematical expression of that made up of different sinusoids. The example we got to yesterday, shown here, has two component signals. Component 1 two component signals in this one. If we break it into the two components, let's express the equations as here, SA and SB. Signal A and signal B, where signal A is simply a sine of 200 pi t. So for signal A, it has a frequency of what? Signal A on the board, sine 200 pi t. What is its frequency? No? What's its frequency? Sine 200 pi t. If I were to draw a plot, then this is a plot as a function of time, the signal S of t. If we look at component 1, SA of t, the equation is sine 200 pi t. The offset, the phase offset is 0, it's plus 0. There's no offset here, so which means it starts at 0. We would expect a sine to start with. The peak amplitude is in fact 1. It's 1 times sine 2 pi ft, so which means that this point is plus 1 and this point is minus 1. And the frequency of that signal. How many times does it repeat per second? This is one cycle. How many cycles do we have per second with SA? Again, how many cycles do we have per second? Sine 200 pi t. What's the general form? The general form is sine 2 pi ft. Therefore, f is No. general form is 2 pi ft. The equation is 200 pi t. What is f? 100. The frequency of component A is 100 Hertz, which means within 1 second, somewhere out here, there are 100 repetitions. So this occurs 100 times within a period of 1 second. If this is 0, then 1 is somewhere out here after 100 repetitions. And the period of a single cycle is simply the inverse of the frequency. If the frequency is 100 Hertz, 100 cycles per second or repetitions per second, then the period is 1 divided by 100 seconds. Or 0.01 seconds. That's the duration in time of one cycle. So if this is time 0, then this would be time 0.01 seconds, 0.02, 0.03, up to 1 second, and we'd have 100 repetitions within that 1 second. Second component, SB, peak amplitude of 1/3. So it'd look the same, except it's shrunk in this way, so that the peak would only go up to 0.33 and to minus 0.33. Phase offset is still 0. Frequency of component B is frequency of component B. Frequency of component A is 100 Hertz, so B is not 200, 300 Hertz. Just relate these two equations. 2 pi ft equals 600 pi t, therefore f is 300 Hertz. So it'd be the same as this, except shrunk, because of the peak amplitude is 1/3, and there would be 300 repetitions per second. So it would also be compressed this way or squeezed in this way. So there'd be many. Can I draw it? Something like that. Not very accurate, but we'd have 3 cycles when this has 1 second, because this second component is 3 times the frequency. When we create a resulting signal, if we just add them together, which is what we've done here really, sine 200 pi t plus 1/3 sine 600 pi t. For now, just ignore this 4 over pi. We just added them together. Then we'll get some different shaped signal. And importantly, the frequency, if the components have frequencies which are integer multiple of one of them, this equals 1 times 100 Hertz, and this equals 3 times 100 Hertz. So the components have frequencies which are integer multiples of this one. That is, FA is 100 Hertz, FB is 3 times FA. If that's the case, then the resulting signal, when we combine them, is this original fundamental frequency, 100 Hertz. And the resulting so therefore the resulting signal has a frequency of that fundamental frequency. And that's illustrated here. The 2 components, the first component and the second component with a smaller peak amplitude and a higher frequency, add them together, and we got the equation on the previous slide, plot it, and you get this. It's no longer our simple sinusoid, it's a combination of two. And you note the frequency of this, one repetition is the same as the first component. Adding the two together, the frequency of the resulting is the same as the fundamental frequency. Be careful that this plot uses the general form of the equation where it says 2 pi ft. It doesn't give us a value of f. In our equation on the previous slide, we said f was 100. This plot doesn't show the value of f equal to 100. But the same frequency of the resulting signal as this component signal. And the period of this is the same as the period of this. And when people design communication signals that our wireless LAN transmits or our Ethernet card transmits, what are the signals it transmits? They design them using these concepts of simple sinusoids and combining them together to create some signal that of a shape that they want. You can combine them in different ways to get different shaped signals to transmit. This is a plot of our resulting signal, but in the frequency domain. We said that we can view signals from a time domain like this. As time changes, the signal intensity changes, or in the frequency domain, shown here. This specifies the peak amplitude of the component frequency. So this is the same signal as the bottom of the previous slide. Let's see what it shows. It shows the peak amplitude on this axis and the frequency on this axis. Let's try our component signal. What do we have? When we added these two together, we got sine 200 pi t plus 1/3 sine 600 pi t. One component, the second component, add them together and we get a signal shaped like this one. So looking at this signal, signal C, there are two components. The first component has a frequency of 100 Hertz. The second component a frequency of 300 Hertz. The first component has a peak amplitude of 1. The second component a peak amplitude of 1/3. So what we can do is view it in the frequency domain, where we have on this axis the frequency of the components and here the peak amplitude. It's an uppercase S. Component 1, frequency 100 Hertz. And what we do in the frequency domain is draw an impulse where we have a component of frequency 100 Hertz, an impulse of the height of the peak amplitude. Peak amplitude of this is 1. So we have an impulse that goes up to 1. The second component has a frequency of 300 Hertz and a peak amplitude of 1/3. So at 300, this plot with two impulses is a plot of this signal, which is just the same as this signal. It's just a different way to view it, the same information. So this is the signal plotted in the time domain. This is the same signal plotted in the frequency domain. If we consider a signal as made up as the summation of sinusoids, like this one, just one sine plus another, then in the frequency domain, the plot takes each component, takes their frequency, 100 Hertz, the peak amplitude, 1, we have an impulse, and in the second component, frequency of 300 Hertz, here, peak amplitude of 1/3, and we have an impulse, and that's our plot of our signal. Why do we do that? So we have 3 representations of that same signal. A plot in the time domain, an equation, a formula, and a plot in the frequency domain. It turns out for people who need to design and analyse signals, looking at them in the frequency domain can be much simpler. If I give you this equation in the quiz, you should be able to plot this. Plotting this may not be so easy. You usually need a calculator to know where are the peaks and troughs here, what are the exact values. Plotting this is easy. You simply identify the frequency of the components, 100 and 300, the peak amplitude of the components, 1 and 1/3, and you plot 2 impulses. So it's another view of how we can look at signals and how people design and analyse signals for real communication systems. Any questions on how to create such a frequency domain plot? We can get some more information from it shortly, but let's make sure people know how to obtain that plot from the equation. Quiz next week. If I give you the equation, you can create a frequency domain plot. Maybe I want 100%. You can? Not so hard. The point is, alright, you need to remember what the plot is, but you need to identify the components, the frequency of those components, and the peak amplitudes of those components. And then we just get that each component is represented by an impulse at that frequency with that peak amplitude. This is just another example. The examples on the slides don't use an absolute value for f. They use a variable. In this example, I used an absolute value for f equal to 100. That's the difference here. Here it's 1f instead of 100 Hertz. This is just a generalization of what we see on the board. Of course, life is not so simple that we have a communication signal which is a sinusoid or the addition of sinusoids. It can be much more complex. Here's an example of a frequency domain plot of a signal. It's not simply a set of impulses, it actually becomes continuous over time. So in practice, they're not this simple, but the same principles apply. Now we can obtain some definitions of important terms that we need to know to characterize different signals. A signal has some spectrum, and the spectrum of a signal is the range of frequencies it contains. So our signal SC of t has a spectrum. It contains 2 components, one with a frequency of 100 Hertz and another with a frequency of 300 Hertz. So in our very simple example, the spectrum of that signal is 100 Hertz and 300 Hertz. The absolute bandwidth is the width of that spectrum. It's the difference between the minimum frequency component and the maximum. In our example, signal SC of t, absolute bandwidth is the difference between the minimum frequency and the maximum frequency in the spectrum. In our case, 200 Hertz. Maximum 300 Hertz, minimum 100 Hertz, absolute bandwidth 200 Hertz. For now, alright, I will say some signals may contain a component with zero frequency. In that case, we say it has a DC component. We generally want to avoid such signals. Let's stay with these two terms and give you some more examples. Let's say SD of T, another signal. Here's another signal. What is its spectrum? And what is its absolute bandwidth? See if you can work it out. And then we'll find a volunteer to tell us the answer. There's the signal, 3 components, almost the same as the previous signal. The first 2 components are sine 200 pi t plus 1/3 sine 600 pi t plus 1/5 sine 1000 pi t. What is the spectrum of this signal, and what is the absolute bandwidth of this signal? How about the spectrum? The spectrum is the set of frequencies contained in that signal. How many components?
3.
What is the frequency of the first component?
100.
100 Hertz.
Yes.
Second component?
300.
Third component?
5.
500 Hertz. That's it. There's our spectrum. This signal contains 3 components of 100 Hertz, 300 Hertz, and 500 Hertz. That's the range of frequencies contained in that signal. Why 500? Well, 1000 pi t, the general form is 2 pi ft, f must be 500. The frequency of this component is 500 Hertz. So what's our absolute bandwidth now? Absolute bandwidth. We have our spectrum. What's the absolute bandwidth of this signal? The bandwidth, which is if we look at those 3 components, we have 100, 300, 500. The bandwidth is really the width between the minimum and the maximum component in Hertz. So it is minimum is 100 Hertz, maximum is 500, therefore the bandwidth is
300.
maximum, minimum, 5 take 1 equals 4. The absolute bandwidth of this signal is 400 Hz. Now, next task, and you can do it, draw a plot of that signal in the frequency domain. So everyone, draw on your spare piece of paper a plot of that signal in the frequency domain. What is this? What is this value? 1 divided by 5. Okay, good. Okay, good. Okay, some people are getting it.
What's the fundamental frequency?
Your plots, remember, for each component, we take the frequency of that component and the peak amplitude of that component and draw an impulse at that frequency with an amplitude of the peak amplitude of that component. This is the plot of this signal, which had 2 components, therefore has 2 impulses. You're going to have 3 impulses for this signal with 3 components. Some people have got it. Okay, good. Alright, let's see the result. 3 components with frequencies 100, 300, 500 Hertz. 100, 300, 500 Hertz. First component has a peak amplitude of 1. It's 1 times sine 2 pi t. Therefore, we just simply plot an impulse at that frequency with that amplitude. Second component, frequency of 300 Hertz, peak amplitude of 1/3. Third component, frequency of 500 Hertz, peak amplitude of 1/5 or 0.2. So that's it. That's the plot of this signal, but in the frequency domain. Now draw a plot of that signal in the time domain. the signal as a function of time. Don't attempt. It's not easy. You need a calculator, because if you want to plot that as a function of time, okay, at t, actually it'll go down here, at t equal to 0, you plug in t equals 0, 0, 0, 0, all right, it's going to start here, and then it's a next value of t, maybe 0.1, you plug it in, you take the sine of 200 pi times 0.1 plus the sine of, or 1/3 the sine of 600 pi times t equal to 0.1, and so on. You get some value here, and you get many points. Not easy to do without a calculator or a computer. And I have some shape, which we'll see shortly, the shape, but it's not so easy just to plot on a piece of paper. This one is. And in fact, from this one, we can extract this information very easily. Given this plot, the spectrum, quite simply, 1, 2, 3 components at 100, 300, 500 hertz. The spectrum is here. Given this plot, absolute bandwidth, take the minimum component, the maximum, the difference. Absolute bandwidth is the width between here and here. 500 minus 100, 400 hertz. So given a plot in the frequency domain, we can look at bandwidth and spectrum reasonably easily. In the time domain, it's not so easy to visualize what those values are. Why do we care about these parameters of spectrum and bandwidth? Because eventually we'll see that they impact on our data rate and other things. So, some signal has a spectrum, the set of frequencies of the components in that signal. Any signal can be, we can think in theory, can be made up of different sinusoids, different components. We could write in theory an equation to represent any signal which has different components which are sinusoid signals. The absolute bandwidth is the width of the spectrum, that is the minimum frequency component, or the maximum frequency component minus the minimum. The range of frequencies that signal contains. Some signals have infinite absolute bandwidth. If we go back, here's an example of a signal in the frequency domain, and it keeps going. We've just limited it to here, but in practice, or in theory, it will keep going up and down. Very small. As you can see, it's very large here, but then gets smaller and smaller and smaller, but gets infinitely small. It keeps going. If we were to calculate the bandwidth of this, well, it's the maximum frequency component, but the maximum frequency component is at frequency infinity. So in fact, it has an infinite bandwidth. That is, the width keeps going. This one is limited to just these three components. This other example would have an infinite absolute bandwidth. But in practice, most of the energy of this signal, because the signal is transmitting energy across some medium, most of it is concentrated here. This is the peak amplitude, remember. So we can think most of the energy is in this area, or in this range of frequencies. Out here, it's getting very small. The peak amplitude is maybe very, very close to 0. It's not 0, but very close. In practice, even if we have a signal with an infinite absolute bandwidth, we will say it has some real bandwidth. And there are some different measures to say what do we cut off. We just ignore the rest here in practice. And also, any transmission medium, a copper wire or an optical fibre, will only support And the transmitter in my computer that creates the signals will only support transmitting a certain range of frequencies. My computer cannot transmit at an infinite range of frequencies. So in theory, although it has an infinite absolute bandwidth, in practice any signal has some real bandwidth. And sometimes called the effective bandwidth, or we will just refer to it as bandwidth. So this absolute bandwidth is more a theoretical concept. When we hear of bandwidth in practice, it means the real width that the signal contains that is transmitted. It's not easy to calculate what this is. We cannot define what the real bandwidth is, but it's a value of interest to us. The bandwidth limits the data rate of our system. Data rate measured in bits per second, bandwidth measured in hertz, there's some relationship. Turns out in general, the larger the bandwidth, the faster we can send our bits, the higher the data rate. We'll show the relationship. So far what you know is signals can be mathematically represented as a composition of sinusoids. We can represent that signal in the time domain or in the frequency domain. The spectrum is the range of frequency components, and the bandwidth, or the absolute bandwidth, is the difference between the minimum component, or the maximum and minimum component. In practice, some signals are more complex than what we've written here, and they may have an infinite absolute bandwidth, but the characteristics of the medium and the transmitter limit the bandwidth, limit the range of frequencies that can be transmitted. And what we'll show now is that there is a relationship between the bandwidth and the data rate. That's one example we can skip. Let's go through this. This top plot shows one of the signals we've seen already. It's very similar to this one. It's just that this plot we use the variable f instead of the value 100. You can see the equation, sine 2 pi ft plus 1/3 sine 2 pi 3 ft. Same pattern as we had here, sine 2 pi 100t plus 1/3 sine 2 pi 3 times 100t. This is just generalized. This is the signal in the time domain. This is another signal with a third component, similar to what we had up there. Sine 2 pi ft, 1/3 sine 2 pi 3 ft, 1/5 sine 2 pi 5 ft. You see the pattern there? We add on another component. The peak amplitude is 1 divided by 5, and the frequency is 5 times f. And this is the plot if we get it in the time domain. What's the difference between the plots? Well, not much, all right. We have multiple troughs and peaks here. It will become a little bit clearer as we add more components. The top one is we add a fourth component, 1/7 sine 2 pi 7 ft. This is if we had an infinite number of components. We keep following this pattern. The next one will be 1/9 sine 2 pi 9 ft, 1/11, 11 ft. Keep adding components. Mathematically, if we do it forever and then plot that, we get a perfect square wave, a digital waveform. So if we think this can be used to represent data, we can calculate what data rate we can achieve with such a signal. How can this represent data? Let's say the data we have is a set of bits. The sequence of bits is the data that we want to transmit. Then one thing we could do is transmit a signal like this, where the signal is +1 for some period of time if we want to transmit bit 1, and -1 if we want to transmit bit 0. And if we want to, so we have bit 1, bit 0, and if we have two bit 1s in a row, then we transmit +1, then +1 again. So that's, I think, reasonably obvious. We could use such a signal to represent binary data. In this case, the signal would look like this. +1, 0, +1, +1, 1, 0, 1, 1, 0, 1, 1, 1, 0. Here's a digital signal that represents this digital data, an example of a digital signal. How do we create this signal? Well, we could use this and we could just alternate what we transmit depending on what's the input bit. How fast can we transmit these bits? That's what we care about. How many bits per second can we transmit? Well, it depends upon our signal. With this signal, which has a period of t, this is one period, we could say transmit 2 bits. 1 bit and then a second bit. So in the period of the signal, we can transmit 2 bits. Let's make note of that. Of any signal in one period, transmit 2 bits. Now, depending on the value of the frequency of that signal, we will have a different period. And it will determine how many bits per second we can transmit. So let's put some numbers to this to see what values we can get for a data rate. This is a general form of our equation that we had previously on this plot. 2 pi ft plus a third sine 2 pi 3 ft. Ignore the 4 on pi at the front. Let's give a value to f. In the slides it uses the variable f. Let's give it a value. Let's say f is, give it a good example. Let's say f is 2 megahertz, 2 million hertz. then S1 of t is the sine 2 pi ft, which is 4 by 10 to the 6 pi t. 2 megahertz is 2 by 10 to the power of 6 hertz. 2 million. Sine 4 million pi t plus a third sine 2 times pi times 3f by 6 million. 12 million pi t. All I did is set f to be 2 million and substitute it into this equation, and we get this. That's our signal, or one signal. It still looks like this. It's just got an absolute frequency of 2 megahertz, 2 million cycles per second. The period, what is the period of this signal? First, before we calculate that, there was a question before I forgot to answer. What's the fundamental frequency of this signal? Well, this component has a frequency of, 4 million pi t, has a frequency of 2 megahertz. This component has a frequency of 6 megahertz. Which is in fact 3 times 2 megahertz. The fundamental frequency of this signal, f, lower subscript f, is 2 megahertz. In other words, the frequency of the resulting signal is 2 megahertz. The first component is 2 megahertz. The second component is 3 times 2 megahertz. Because they're all integer multiples of 2 megahertz, 1 times 2, 3 times 2, the resulting frequency is 2 megahertz. So the frequency of this signal is 2 megahertz. F, that's an F there, the fundamental frequency. Or let's say F1. Signal 1 has a frequency F1 of 2 megahertz. The period of this signal, the period, remember, is simply the inverse of the frequency. The period of this signal is 1 divided by f1. 1 divided by 2 million is half a microsecond. 1 divided by 1 million is 1 microsecond. 1 divided by 2 million is half a microsecond. This is this 1 divided by 2 million, 0.5 microseconds, U. Or remember micro, 0.5 by 10 to the minus 6 seconds. Micro is 10 to the power of minus 6. That's the period of our signal, shown up here, just that this plot uses an arbitrary value of f and t. We've said before, in one period, we'd be able to transmit 2 bits. In this case, even though it's not a perfect digital waveform, we can see that if we have this portion that is high, mostly high, for some period of time, then we could use that to represent bit 1. And if it's mostly low, to represent a bit 0. So with this signal, we could also transmit 2 bits within one period. Transmit 2 bits every period. The period of our signal is half a microsecond. I'll come up here. That's a bit clearer. 2 bits in half a microsecond, the period of the signal. Therefore, 1 bit in a quarter of a microsecond. If we can have 2 in half a microsecond, we can only get 1 in a quarter of a microsecond. Or in 1 second, 4 million bits. If 2 bits can be sent in half a microsecond, then 4 million bits can be sent every second. That's our data rate. With this signal S1, which had 2 components with a fundamental frequency of 2 megahertz, the data rate that we could achieve with this signal is 4 megabits per second, 4 million bits per second. So we're seeing the relationship between a signal and the data rate. What else do we know about this signal? Absolute bandwidth of our signal. What is it? Absolute bandwidth? No idea? How are you going to calculate it in the next quiz? Look at the components. Can you help him? Absolute bandwidth. Signal, 2 components. What are their frequencies? Frequencies are 6 megahertz and 2 megahertz, therefore the absolute bandwidth is 4 megahertz. One component is at frequency 2. First component frequency 2 megahertz, second component frequency 6 megahertz. The difference is 4 megahertz. This signal has an absolute bandwidth of 4 megahertz and can achieve a data rate of 4 megabits per second. And this is the shape of that signal. Let's try another case. In this example, S1 of t, what I did was I took this general equation and I set f equal to 2 megahertz, which gave us a signal with a fundamental frequency of 2 megahertz. Try it again. Sorry, S2 of t, another signal, but let's set f equal to 1 megahertz. Reduce the frequency. We get the same type of equation. Sine 2 pi, if f equals 1 megahertz, what have we got? 1 million times 2 times pi t plus 1/3 sine 6 million times pi t. It is simply this equation with the variable f equal to 1 megahertz. In this case, we set f to 2. Component will have a frequency of 1 megahertz. Second component will have a frequency of 3 times that, 3f. Fundamental frequency, this component frequency of 1 megahertz, this is 3 times 1 megahertz. The fundamental frequency of this signal S2 is 1 megahertz. The period of this signal is the inverse of 1 million, 0.1 microsecond. So same general form of the equation, I've just used two different values of f. 2 megahertz and now 1 megahertz. Two components still, 1 megahertz, 3 megahertz. Fundamental frequency is 1 megahertz, because this is 1 times 1, this is 3 times 1. Period is the inverse of the frequency. 1 divided by 1 million is, sorry, that's wrong, 1 microsecond. 1 divided by 1 million is 1 microsecond. That's the period. Applying the same principle, we can transmit 2 bits every period. 2 bits can be transmitted in 1 microsecond, then in 1 second, if we can send 2 bits in 1 microsecond, in 1 period, then we can send 2 million bits in 1 second. Why can we send 2 bits in 1 microsecond? Our period is 1 microsecond. The period is the time from here to here. Think as this is 1 bit, and this is another bit. We have 2 different signals now. S1 of t and S2 of t, same shape if we plot them. They both look like this, except they have different frequencies. The frequency of S1 of t is 2 megahertz. The frequency of S2 of t is 1 megahertz. I should have done the other way around, but that's okay. This signal with frequency 1 megahertz gives us a data rate of 2 megabits per second. This signal with a frequency of 2 megahertz gives us a data rate of 4 megabits per second. This signal has an absolute bandwidth 3 minus 1 of 2 megahertz. We've changed the data rate simply by changing the frequency of that signal. In general, increase the frequency, keep everything else the same, you'll increase the data rate. Frequency 1 megahertz, data rate 2 megabits per second. Increase the frequency to 2 megahertz, increase the data rate to 4 megabits per second. Double the frequency, double the data rate. We want higher data rates generally. But also, when we doubled the frequency from 1 up to 2, we doubled the bandwidth. The bandwidth went from 2 up to 4. Increasing the bandwidth increases the data rate. We want high data rate. We want to send as many bits per second as possible. But unfortunately, bandwidth costs us money. We want to minimize bandwidth. So we have a trade-off that arises. Our signal in both cases, we use this general form of the equation where we had 2 components. What happens if we use 3 components? What's the difference? Why do we care about 2 components and 3 components? We can think the more components here, the more accurate the signal is. Remember, we're using this to represent a bit 1 and this a bit 0. The ideal signal is this one, where bit 1 is represented by a signal that is always at the level 1 and bit 0 always at -1. A digital signal. This is ideal. we need an infinite number of components to get this. If we use less, then our signal that we transmit and as a result the signal that we receive will not be the same as the ideal signal. And although it's hard to visualize, what can happen if we transmit a signal which is not close to this ideal signal, it's easier for errors to be interpreted by or to be incurred by the receiver. The less components, the more likely errors will arise. One last case. S3 of T, a third signal. Let's say instead of using 2 components, we use 3 components. F at 1 megahertz, using this equation, it'll be sine 2 pi 1 million t, 1/3 sine 2 pi 3 million t, plus 1/5 sine 2 pi 5 million t. Sine 2 pi 1 million times t, plus 1/3 sine 2 pi 3 million, plus 1/5 sine 2 pi 5 million. All I did is to substitute it into this equation, f equal to 1 million, 1 megahertz. 1 million, 3 million, 5 million. Frequency of this component is 1 megahertz. Second component is still 3 megahertz. Third component is 5 megahertz. 5 million. The fundamental frequency of this signal, we have components 1 million, 3 million, 5 million. The fundamental frequency is still 1 million. One megahertz. If the frequency is 1 megahertz, the period is 1 microsecond. Identical to this, frequency 1 megahertz, period 1 microsecond. 2 bits in 1 microsecond gives us a data rate of 2 megabits per second. We haven't changed the data rate. These two signals, same fundamental frequency, 1 megahertz, same data rate, 2 megabits per second. What has changed? Absolute bandwidth. This signal has 3 components, 1, 3 and 5 megahertz. The absolute bandwidth is the difference between the maximum and the minimum. 5 minus 1, 4 megahertz. So comparing these two signals, the first one has 2 components, frequency of 1 megahertz, data rate of 2 megabits per second. The second one, an absolute bandwidth of 2 megahertz for the first one. The second signal has 3 components, same frequency, same data rate, but a larger absolute bandwidth, 4 megahertz, because it ranges from 1 up to 5. What have we done? The second signal has a disadvantage in that it uses more bandwidth. We'd like to minimize bandwidth. It has a disadvantage in that it uses more bandwidth. We get the same data rate between the two, but it has an advantage in that it's more accurate. This more accurately represents the perfect digital waveform than this one. It's slightly closer to all +1 than this one. Increasing the number of components here will increase the accuracy of our signal, reduce the chance of errors. But increasing the number of components increases our absolute bandwidth. That's a negative. Increasing accuracy is a positive. We'd like to do that. Increasing absolute bandwidth is a negative because bandwidth costs money. There's only a limited bandwidth available, or a limited range of frequencies available. You may have to pay for a license to use some frequencies, and that costs money. There's a cost incurred of using a larger bandwidth. We'd like to use a small amount of bandwidth as possible to get as much accuracy as possible and as much data rate as possible. There's no single simple solution. There's a trade-off between all of these factors. Comparing this one to this one, same accuracy, that is identical shape of the signal. 2 components in this one, 2 components here. This signal gives us a data rate of 2 megabits per second, uses a bandwidth of 2 megahertz. This signal gives us a data rate of 4 megabits per second. That's good. But it uses more bandwidth. That's bad. So these 3 cases have shown the trade-offs that arise. We need to design a signal such that gives us high data rate, low bandwidth, and high accuracy. And there's no single solution. You need to choose whatever's the most appropriate. We have a summary of that. That was the example that we've just calculated. We calculated that example. But we did it under different conditions. Sorry, we did 2 megahertz and 4 megahertz. The example says 8 and 4. That's okay. This is the summary of those trade-offs, and then we'll finish. In terms of bandwidth, the range of frequencies a signal uses, we have some limit on the signals, on the frequency that we can transmit. The bandwidth is a limited resource. You cannot use an infinite bandwidth. The greater the bandwidth that we use, the greater the cost of our transmission system. Therefore, we'd like to minimize the bandwidth use. In terms of data rate, the data can be approximated by the signal. As we saw there, we could use this when the signal is high, represent bit 1, when it's low, bit 0. The greater the bandwidth, the greater the data rate. One thing that is not so easy to visualize, but also important, is accuracy. The receiver, when it receives a signal, must be able to interpret what it means. Does this signal mean bit 1, or does it mean bit 0? Especially when there's noise and errors in the communications medium. So when people design signals, they need to trade off these different factors. They want to get high accuracy, therefore less errors, high data rate, but minimize the bandwidth in use, and therefore minimize the cost. And people design signals using the mathematics similar to this, but much more complex, and allows you to choose a trade-off that's most appropriate for your system. That's a good place to finish. So what we've tried to do is to explain how communication signals can be thought of as being composed of sinusoid signals, what is bandwidth, what is spectrum, and show the relationship between data rate and bandwidth and frequency and accuracy. And we showed that with three examples or three cases of different signals. Try to identify the trade-offs. Have a look at these calculations. Make sure you know how I went through those steps, especially the last two I went through quite quickly. Try to get one of them, make sure you can get the same answer, and make sure you can calculate for the other two, or any combination. You also know that if we look in the frequency domain, those plots of the peak amplitude versus frequency, it can be sometimes easier to analyse than in the time domain. Let's finish there, and then on next week we'll look at some other parts of how to transmit data, what causes errors, and finalise with some equations to give us a more precise relationship between bandwidth and data rate. Enough for today.